We have already encountered one example of an efficient sort, which is the heap sort. The heap sort is a priority queue sort with a heap implementation of the queue. The merge sort and quick sort are two other efficient sorting algorithms. Both of those algorithms are considered divide and conquer algorithms. The reason is that these two sorts first divide the list into two possibly unequal halves, and then the two halves are recursively sorted. To analyze the efficiency, it is helpful to examine the recurrence equation. The simplest case is when the halves are equal. In that case, the recurrence equation states that t of n is 2 times t of n over 2 plus n. The first part results from the fact that it is divided in two and both halves are processed. The addition of n is because the action performed on the halves involves all the elements. The initial condition states that a one-element array can be processed in constant time. The solution to this recurrence equation is big O of n log n. Although it grows faster than linear because log n grows so slowly, it doesn't grow much faster than that. Most importantly, it grows much slower than a quadratic function. Let's start with the main characteristics of the merge sort, which is the simpler of the two. The merge sort divides the array into equal halves, and then it makes two recursive calls on each half. After the recursive calls, it merges the two halves. Because the recursive calls are done first, the merge operation happens on the way out of the recursion. It continues to divide the array in half until it reaches the base case of a one-element array. Then it merges the one-element arrays, then it merges the two-element arrays, and so on. Let's watch an animation of this sort. So when we run the merge sort, what we notice first is that the one-element arrays are merged into two-element arrays. Now we have two two-element arrays that are being merged into four-element arrays. And one thing this animation is showing is that it's actually going to make a copy when it copies them back. So now what we have are two four-element, well, in a moment we'll have two four-element arrays, and those two four-element arrays now are being merged into an eight-element. And so this process will continue to the next pair of 8, which will then go into 16, and it will continue until the entire array is properly sorted. Okay, having seen how this sort behaves, let's summarize the efficiency issues. Because the array is always being divided into equal halves, the average and worst cases are the same. For time, it is the n log n big O we characterized as the solution to the recurrence equation. The stack space needed is log n, because for an array of size n, we only need to divide it in half log n times to reduce the size to 1. Keep in mind when we say log n, we mean log base 2 of n. Because the quicksort is a bit more complicated, we will examine its code, starting with the main method. As is so often the case with recursive methods, the method sort is the helper method that gets the recursion started by supplying the lower and upper bounds of the array as the initial values of the parameters left and right. The recursive method is given the bounds of the subarray to be sorted. The base case is an array with no elements. A call is made to the find pivot method that we will examine shortly. It returns the division point. Then the array is divided using that division point, and the two halves are recursively sorted. The find pivot method contains the essence of the sorting mechanism. Like the recursive method, it has provided the array and the bounds of the subarray. In this implementation, the first element of the subarray is chosen as the pivot. In some implementations, the pivot is chosen at random. The goal is to divide the subarray into two halves. The left half will contain values less than the pivot, and the right half those greater. The loop continues while there is at least one element remaining. This loop moves left forward as long as the values on the left side are less. The next loop moves right backward as long as the values on the right are greater. Then the values at left and right are swapped to ensure what is on the left is less and what is on the right is greater. At the end, the pivot is placed in the middle between the two halves, and the division point is returned. Let's summarize the general characteristics of this sort. We observed that it divides the array into those less and those greater than the pivot value, which in our implementation is the first value of the subarray. Because the call to find pivot comes before both recursive calls, that operation occurs on the way into the recursion. So let's watch an animation of this sort. We'll make a new array, and then what you should notice here is that black horizontal line is what we're using as our value of the pivot. You'll notice that it is the height of the leftmost bar. And as this is proceeding, what's happening is everything on the left is smaller than that line, and everything on the right is greater than it. And at that point, where you now see one red bar in the middle, what that means is that one value is in its proper position. Everything to the left is less, everything to the greater is right. So this is going to happen one more time. So at this point, again, that second red bar is in its proper position. And you'll notice it's beginning to happen more quickly. So all the red bars are now in their proper position. So in this subarray, again, what will happen is as soon as everything on the left is less, everything on the right is greater, the one red bar you see was placed between the two halves. And of course, this operation continues until the entire subarray is sorted. For this one, it happens fairly quickly, which is why quicksort is one of the best sorts to use. And so very shortly we would see that the entire thing would be fully sorted. Okay, so let's watch it just for one more short time, because it will be sorted very, very quickly now. And so finally the entire array is sorted. So having watched that sort in action, let's summarize the efficiency issues. Because the array is not necessarily divided into equal halves, the average and worst cases are different. Because we chose the first element as the pivot, the worst case will be when the array is already sorted in either ascending or descending order. In that case, the array is split at the end, which makes the worst case quadratic for time. Although it requires a complicated analysis, it is still n log n in the average case. For the same reason, the memory efficiency is linear in the worst case, because the number of times it needs to be split will be proportional to the size of the array.